So we have looked at this principle of virtual power, which is framed in the current configuration or the deformed configuration. So it is possible to derive a principle of virtual power which is defined in the reference configuration. There are a couple of ways to do that, but what we will do is, since we have derived this already, we will try to transform it into the reference configuration. So let's take the internal virtual work. Remember, as I have mentioned so many times before, that this is actually an identity. From starting from the left side and taking the equation of equilibrium and the Cauchy's relation into account, you can derive the right side. So the only condition is the velocities satisfy the essential boundary conditions on omega u. Apart from that, delta v is a completely arbitrary function. So let's start from the internal virtual work, and internal virtual work is given as sigma ij delta dij d small v, so over omega, and this can be written as over omega naught. I can use d capital V equal to j d small v and write it as, d small v equal to j d capital V, and write this as j times sigma ij d capital V over omega naught. Now, we have derived this relation before. We have derived the relation that E dot is equal to F transpose dF. So we have derived this relation between the rate of stretch d and the time derivative of the green Lagrange strain. So starting from this relation that we have already derived, we now want to derive delta E dot, and remember, we are doing a equation of virtual power, which means that we have to take this first variation in the direction of delta V. Okay, so when you take the variation in the direction of delta V, remember what delta F was. Delta F was equal to the gradient of delta U when it was taken in the direction of delta U. However, delta F in the direction of delta V is zero, because F does not vary if you vary V. In other words, if you make an error in the velocity, it does not cause an error in the deformation gradient tensor right away. So when you do this, you have to treat F as a constant, because F in the direction of delta V, the variation of F is equal to 0. So this will simply become F transpose delta D F, which means that delta D will be equal to F minus transpose delta E dot in the direction of delta V and F minus inverse. Now I will drop this delta V, this direction indicator delta V, because we are doing principle of virtual power, and it is understood that we are taking all variations in the direction of delta V. So so this is what we have, which means that sigma ij delta dij j d capital V over omega naught, this part can now be written as sigma ij, and then this has to be written as delta dij, and this delta dij will be let's erase this. So in place of this, we'll use this expression. So we'll write it as F inverse K I delta E dot let's say Km and F inverse Mj. That's what we get. We can club these and then we have a J at the front. So we are writing for this part. So we can club this F's and sigma together. So we can write this as J sigma J F Ki inverse F Mj inverse E Km. And from the relationship between S and sigma, which again we have derived before, this is S. So S, let's say Km would be J times F inverse Ki sigma I j. Now I'm using I as a repeated index because that's what is done here. So sigma ij F Ki inverse and then F inverse Mj. So this is exactly what we have here, and therefore this is Skm. And so this term now becomes over omega naught S dot dead with E dot D capital V. So the internal virtual work can be written either in terms of sigma and D in the deformed configuration, or S and E dot in the undeformed configuration. What about this quantity? This quantity is easy because this quantity is easy. It's bk delta vk dv. So I can convert it into j bk delta vk d capital V. This we have defined already as bk0. So this becomes over omega naught. This becomes b0 delta v d capital V. Here you have to remember this delta v is in terms of the reference coordinates. So it is delta v as a function of capital X. Okay. Now this can also be converted using Nansen's relation, using the relation between this traction in the in terms of the second peak stress and the tractions Tn. So to deal with this term, we can take the help of the Nansen's relation. So we can write this as over del omega naught. So we can write this first as sigma times n. This is the traction due to the Cauchy stress, and then we can write it as first over del omega sigma n dot delta v ds and convert it to del omega naught, so that n ds is j sigma n ds is f minus transpose capital N dot delta v d capital S. Now if I just multiply this with f and f inverse, then I have f inverse so this thing along with this j is equal to S. So what I have is f times Sn dotted with delta v d capital S, and Sn is the traction due to the second peak stress. So f, let's say T naught, is the traction due to the second peak stress. So this term becomes this. So this is the last term here. And remember, for the second peak stress, we pull df back as f inverse. So df naught is actually f inverse df. So this is the idea from which the second pk stress is derived. So that is why you get the ft naught here. So ft naught is the real traction that you need to put in here when you are using the second pk stress, where t naught will be calculated from s as s times n. So this will be calculated from s times n. Okay, so this is how we can convert from one formulation to another, virtual power from one formulation to another, and we get an equivalent identity, which is an alternate weak form. So if we want to do what is known as total Lagrangian formulations, we start with a mesh on the undeformed configuration, and this would be, in that case, our starting point. If we do an updated Lagrangian approach, we start with meshing the deformed configuration, and then this would be our starting point. So these are all principles of virtual power. We can derive other kinds of weak forms, which we will look at in the next lecture. Well, there's another way to get the weak form, and that is to start from, say, one of the governing equations. So we can start from the governing equation of equilibrium, and let's do it in terms of this first pk stress. So we know that in terms of the first pk stress, the equilibrium equation is plus bi0 equal to 0. This is the equilibrium equation for a static problem. And now what we can write is we can multiply both sides by an arbitrary function, let's say ui, and it still remains equal to 0. Now if we integrate it over the whole volume, it still is equal to 0. So this is again obvious conclusion from the fact that this equilibrium equation is valid at each and every point. So this is what we have done, basically is the reverse of the localization argument that we used. Now from this we can start applying the divergence theorem. So for the first term, which is omega naught del ui del pij capital Xj dv, we can write it, as we have so many times before done, as a term which is a complete differential. So we can write it as pij del ui minus minus del ui del capital Xj pij and d capital D of that. So these two terms together will give you this. So we have just written this in this split form. So the first term is amenable to the divergence theorem. So this becomes pij capital Nj, because we have d capital V, we are integrating over omega naught. So this is pij Nj del ui ds plus, minus omega naught capital Xj pij dv. Now this is obviously the traction T0 due to the first pk stress. So this is the traction associated with the first pk stress, and so this is the ith component of that. So what you have is Ti0 dot del ui. So we have T0 dot del u d capital S over d omega naught, and then we are left with this term, which is del ui del xj pij dv. Okay, so now okay, please don't confuse between this traction and the traction we met in the previous lecture, which was this. This is the T naught is the traction arising out of second peak stress. So T naught is S times N, and T naught is S times N when you use these combinations of stresses and virtual strain rates, whereas in this case, this T naught arises from P times N because we are working with the first peak stress. So these two T naughts are different. I'm using the same symbol. I should not probably, but I actually am running out of symbols quite fast. So I'll call this T naught anyway, and hope that there would be no confusion. This T naught has to correspond to the stress measure that you are using on in the internal virtual work. Now, let us look at this term del ui del xj times pij. So you have this term which is delta ui del capital Xj pij dv, and this term can be written as, so this can be written as pij p times just make sure you understand that this is p inner product with nabla 0 of delta u. This term is nabla 0 of delta u, but we already know that delta f in the direction of delta u is equal to this. So this is nothing but your delta f. So what you end up with is p so multiplying the equilibrium equation in the reference configuration with an arbitrary function which we think is a variation in displacements, we have now expressed the first term here as this is one term in this first combination, minus we have p times delta f dv. That's the second term. This term is left, so write that down as b0 dot delta u dv. That is equal to 0. So we can take this the other side. So our virtual work equation now becomes this. So this is a virtual work equation in the reference configuration, as opposed to this one, which was a virtual power equation in the reference configuration. Of course, we could have started from the equilibrium equation in terms of the second peak stress and B naught, and done the same procedure and derived the principle of virtual work. And in that case, this would have been the result of that. I leave that as an exercise. And there, please remember that this T naught is going to be F times the traction that you get by doing S times N. So this T naught would be equal to F times S times N, because we have used the second peak stress on the left hand side.